Okay, hi. In case you don't know, I'm Tatiana, this is Chris, and we are going to talk about MLIR. But before we talk about MLIR, we are going to talk about TensorFlow. If you don't know what TensorFlow is, it's a framework for machine learning, tons of users, very complex, runs on everything. So how do we build a compiler for TensorFlow? We already talked about once, a few months ago. This talk has much more information, so if you've been to the previous one, you're not going to be bored here. So MLIR is an intermediate representation. So Chris, please tell us, why did we decide to build a new intermediate representation?
This is a good question, and obviously I have issues here, so I'll try to explain some of this. So as I think lots of people here know, compilers get broken down into different pieces. Clang, for example, generates an AST, and then it produces LLVM IR, and it lowers that to machine code. This is leaving out some things like selection tags. We'll not speak of those here. The interesting thing about this is that LLVM IR and the machine instruction IR are SSA, 3-address, control flow graph representations, and they represent different levels of abstraction. And so the LLVM representation, I call it the C with vectors abstraction. The machine instructions are the assembly abstraction for whatever target you're going for, and you do optimization, high-level optimizations on one, quote-unquote high, and then register allocation scheduling and other lower-level optimizations on the other. And this design has been really good, I think. It has allowed lots of reuse with the back ends, with LLVM, lots of different front ends. And so we've seen that with other people building things on top of the stack, of course. And so I like to point out the Azul JVM as a great example of this. And Java and C are quite different languages, and these Azul folks have figured out every little trick to cram high-level information into LLVM, whether it be metadata or intrinsics or other creative hacks, that well-known functions, all that kind of stuff. And they've put a lot of energy into doing that. They've been quite successful. It's impressive work. Other compilers, for example, the Swift compiler, don't work so well if you go with that approach. Swift is a much higher level language and needs things like generic specialization, closure optimizations, reference counting optimizations, things like that. And LLVM IR is just too low level to really adequately support that. And so in the case of Swift, it has this high level IR called SIL. And what is SIL? It's a 3-address SSA code control flow graph representation, but it has a Swift-specific type system and Swift-specific operations. And so otherwise, it's kind of the same thing. And if you look at Clang, really Clang should have one of these things too. We'll talk about this a little bit later, but it turns out C++ has shared pointers, it has STD vectors, it has all these things that if we had data flow information, we could actually optimize. But if you lower to LLVM, you lose a lot of the information you need, and all the ABI lowering and all that kind of stuff gets in the way of doing these high-level optimizations. But anyways, continuing, Swift isn't unique in this respect. The Rust compiler, the Julia compiler, lots of these newer languages use a high-level IR to do language-specific optimizations. And so this is becoming a very standard thing. Now, if you look at TensorFlow, coming back to the point of the talk and the genesis of this work, TensorFlow has its own high-level operations. It has its own abstractions. And the most important part for the purpose of this talk is the notion of a tensor domain. And so there's tensor operations, which is in XLA in particular, and then lowering to LLVM. Having this abstraction gives you the ability to do high-level, like matrix optimizations at this high-level representation, and then codegenning to LLVM is still surprisingly difficult. So, do you want to dive in?
Okay. So, building domain-specific IRs is really not an easy thing, and this is what we need here. We need to build an IR which will support high-level domain-specific optimizations. Of course, we want to have an SSA form. We wanted to pass the muster of the compiler people, so we need location tracking. And it's really not, there is nothing out there which would give to us out of the box, because all these wonderful things that Chris talked about, they are all specific to the system for which they were built.
And there's a tremendous amount of re-implementation, huge amount of expense building and stuff. Not everybody prioritizes the infrastructure, and so it's not evenly excellent. And I think the bigger issue is that innovations in one space don't benefit everybody else. But the idea of lowering is a pretty proven idea at this point. right?
Okay, so now if we look into what is happening in TensorFlow, it's not like there is one compiler in TensorFlow that would be good. There are many different compilers. And each of them does things in its own way because they are slightly different from anything else. And surprise, some things are really simple. So each arrow here probably has common sub-expression elimination. Some things like TensorFlow control flow semantics, once you start talking about it, it's really complex, and almost nobody does it correctly. So what we need is a single system where things are done correctly, things are done right, and again, how do we build such a system? What is the framework for which we can use it?
Yeah, so we're not going to just put 6 of these out there. We have 6 different things we have to make better, but we're not going to just copy and paste SSA optimizers. And so that leads us to why we're here today. So what is MLIR?
Okay, it's mid-level intermediate representation.
Is it mid-level?
Yeah, oh, sorry, machine learning.
Oh, I thought it was Moore's Law.
Oh, of course, because it's heterogeneous. Okay, multidimensional loop.
Yes, oh, polyhedral's cool.
Yes.
I don't know, I think that we can find something else that it means. Maybe multi-level.
How about we have a competition after the talk?
That'd be great. We could have a student research competition on what it means. So what is it though? What is it really?
Well, it's an intermediate representation, and we took a lot of good things from LLVM. So if you look at it, you'll it looks familiar, and that's on purpose, right? SSA, module, function, block, operation, well, in LLVM it's instruction, but it's very similar.
Yeah, and so there's lots of great things about LLVM. And so all the good things we brought forward. The type system, we're working in the tensor domain, and so we've extended the type system. Of course, you have integers and floats and vectors, but we have multidimensional vectors. And if you want a 4-dimensional vector because you have an accelerator that likes 4D vectors, that is fine. We have tensors. Tensors are n-dimensional arrays, and you can have fixed size arrays, you can have dynamically shaped dimensions, lots of other stuff going on here, quantized integer types. One of the things we'll talk about later is the type system isn't hard-coded. It's fully extensible, and we'll talk about why that's important a little bit later.
Okay. MLIR has open operations system, and that means we don't have any special privileged operations. We don't have target-specific intrinsics. We don't have target-independent intrinsics. We just have operations. And operation can be defined without specifying anything about it, just specify the name in the quotes and arguments. Or we can actually define operations with a lot of properties which allow us to work with them nicely.
Yeah, and the sad cat up there is saying, like, why is add in LLVM an instruction, but add with overflows an intrinsic? This doesn't make sense, right? B-swap is not important enough to be an instruction, really? So if you look at the way this works out in practice, the operations in MLIR, aka the instructions, have an opcode, and they all have source location information. We'll talk about that later. And so the general unifying principle of an instruction is familiar, I hope. So you have some number of SSA results and operands. So you can have multiple results, which is very nice. It also has operands for branches and things like that, so you can branch to a basic block. One of the biggest differences between MLIR and LLVM is that you have attributes, which are these known constant values that kind of like the IMARG stuff in LLVM recently, but it provides a much more structured way to have configuration of the operations. Here are some examples of instructions, but there's obviously lots.
Okay, so I'm going to walk you through the example of an operation. It is TensorFlow fused batch norm. You can see it has 5 arguments, and the types of these arguments are specified afterwards. Question mark means dynamic dimension. So we support both dynamic dimensions and dynamic ranks. Results are also fully typed. And if you notice, %0:5, this is not a tuple. These are 5 separate results, so we don't need to extract anything from tuples to operate on them. We have attributes. These are immutable properties, which come very handy in machine learning programs, which is similar to LLVM, IMARG, but have much richer type semantics.
So the point of all this is that when you say that instructions can be anything, what it gives you is it gives you this multi-level design point. And so we can represent different levels of abstraction and do lowering within one IR and one infrastructure. And so here we can start at the TensorFlow level, which is wild and crazy and has all kinds of extensible things on its own. Lower to XLA, which is a more principled compiler representation with, that focuses on tensors in particular. LLVM, which you all know, maps directly into MLIR as well, and so we can do lowering within one framework, and we don't have to have a different implementation of the compiler for each of these stacks. So one of the things you may be wondering, though, is if you do this and you just have strings everywhere, don't you get the JSON or the XML of compilers? And so now everything is stringly typed, and you're using get operand 17, and nothing, there's no structure in the universe? Well, actually, no, we can do better than that.
Well, there is structure, and it's called dialect. So because we have very flexible operations, we need to define them in some more structural ways than just names. They are grouped. The group of operations is called dialect. Dialects can have custom types. They can have customization hooks. So if, for example, we want to call into TensorFlow to do constant folding, we just do it via TensorFlow dialect. And then we also define functionality for each operation. And for dialect, we can have custom printer, custom parser, verifier. So although we have operations with just strings as names, once you look at IR, you would never guess it.
And so one of the cool things we kind of glossed over early is this idea of nested regions. One of the really cool things about this representation is that you can have subgraphs attached to an instruction. And we'll talk about this. This is really important for representing and transforming high-level control flow. Also things like OpenMP parallel regions, things like closures and lambdas and source programming languages. This is a very cool thing that it makes certain transformations that are very, very difficult in the LLVM world suddenly very easy. And we'll give a few examples of this later. So one of the other things is that we pulled a lot of the great things of LLVM forward. We also fixed a lot of the bugs. We're not going to go into all this, but for example, the pass manager is obviously multi-threaded, right? Running a compiler on one core is not sensible in today's world. So let's talk about the infrastructure. We'll dive into how this actually plugs together.
Okay, so back to the operations. We don't really want to write them all in C++. If you wonder why, last time I looked at TensorFlow, it had more than 900 operations. So we want to make it easy to define new operations, and we do it using table gen. So we can specify an operation. Classes of operations can have its own hierarchy, so that we say this is a unary operation, then it's easy to define the rest of unary operations. Operations can have properties. So for example, if it has no side effects, we define once what it means and then reuse it. It has named inputs and outputs, attributes. The documentation for the operation is part of the operation definition, so that we could generate it. And then there are functions which let you define optimizations and semantics.
Yeah, and so the nice thing about this is there's a single point of truth. And so documentation, of course you generate that from the definition of the instruction. And this is also a good thing because now it forces you to have those conversations about what the semantics of this thing actually are. One of the other things we generate is we actually generate the C++ class that you interact with as a programmer. And so all these operations end up being typed by virtue of being declared, and we have a declarative declaration, but then we get a C++ class that provides the interface that you want. And this is how you get the accessors that are named. This is how you get nice constructor syntax. This is how you get the verifier to be auto-generated from the properties. And so in this case, the operation declared that the result and arguments all have the same type, and so the verifier just automatically checks that. And all transformations can assume that operations are properly structured, which is fairly novel for machine learning frameworks, I think.
Okay. So, of course, we need not just define operations, we need to transform from one set of operations into another. And we have a system which allows you to do it by writing declarative patterns. It is general, it supports M2N patterns. It supports everything that we need to do to express operation transformations in TensorFlow. So for example, you can say that this transformation valid only if attribute has a certain value. And if our pattern matching system doesn't work in declarative way, there is an escape, and you can also code whatever you want in C++.
Yeah, and the goal here is to cover the common keys. So it's a compiler infrastructure, so of course it provides pass managers and passes, it provides walking, it has LLVM style pattern matching for the match pattern stuff.
Okay, we have all familiar tools. We have MLIR OPT. We believe in testing. So it's really easy to write the test. You write the transformation, input, output, and here is test, and it also runs very fast.
Yep. And so one of the things we've invested a lot in is source location tracking. This is one of the things where usually you bring up the whole system, you get tons of users, and then they complain about debugging optimized code sucking. At least that's been my experience. And so instead, knowing that this will be a problem, we've invested right from the start to make sure that it's great and it's required. And every instruction has to have a location applied to it. One of the cool things about this is that then the entire compiler can assume that it has that. And so, for example, you can emit a diagnostic that gets routed to the location that an instruction came from at any point. And so we can use this for testing. And so we have dependence analysis, for example. We have a pass, and it just outputs diagnostics telling us what the dependencies are. This means that now we can use a -verify mode, just like Clang or Swift does, to actually write tests for this. We don't have to write a transformation that uses dependence analysis or uses alias analysis that, through a series of transformations, and because dependence analysis returned the right thing, the right transformation happened. It becomes really nice. And having location information in general is really important when you have transformations or optimization remarks or things that can fail.
Okay. Another tool we have is MLIR Translate. And this is because oftentimes our input and output is some complex format, like for example, protobufs, and we really don't want to write all our tests on protobufs. So we have a tool which allows us to go from something to MLIR and back, and then we can write separate tests for translations, and all the other testing goes on MLIR itself.
Yep. And so, as you might guess, LLVM is really important to us. We co-generate through LLVM, and LLVM is really fantastic in lots of ways. And so we represent LLVM as a dialect in MLIR. And so when you want to do code generation, you lower down to the LLVM abstraction, convert to LLVM IR, and then keep going. And it works just like you'd expect. So let's talk about how the TensorFlow ecosystem is already using MLIR. And this is a really key part of TensorFlow's evolution over time.
Okay. So this is back to the picture of TensorFlow compiler ecosystem, but now we are going to talk about what are we already doing to implement things via MLIR. And in the future, everything here will go via MLIR, which means good software engineering practices, good quality of implementation, location tracking, modular structure, code reuse, no duplication, and complete semantics for everything we do.
So the TensorFlow Lite converter is one of the farthest along pieces right now. The TF Lite converter is basically a little mini compiler. It's mapping from TensorFlow's graph to the TF Lite graph. And these are, as is typical in this domain, similar but different. And so there's lowerings, mappings, quantization algorithms inside of this. And so re-implementing this with a compiler framework is a series of passes, and reusing a lot of the infrastructure we have has made this very nice. And it gives us user-visible improvements.
Yes, and so this is my favorite slide, because when you tell people MLIR, they're like, what is that MLIR thing? Why should I use it? What does it do for me? Well, this is what it does. This is the TensorFlow to TensorFlow Lite converter, which is in use today. If something is wrong with the input, then this is what you see. Converter crashed, and there is a lot of information here which explains whether in the converter it crashed, but it doesn't tell you anything about your model. With MLIR, it actually tells you what is that line of Python code, where there is something which needs to be fixed. And if you ever spend hours trying to fix your program in the complete lack of informative error information, you can appreciate how important this is.
Yes. So another example that we're building right now is a new compiler bridge for TensorFlow. And so in the TensorFlow team, we're investing a lot in XLA, which we'll talk about later. And so we are revamping the way that TensorFlow lowers into XLA to make it more reliable and work better and build on all this infrastructure. Yeah.
And it's not just XLA, because we have a general framework. And really, all what we are doing here is we are translating from one dialect of MLIR to another dialect. We can translate to XLA. We can translate to some other dialect. We can translate from XLA to some other dialect. We now have a general infrastructure, which makes it really easy to take TensorFlow and plug in some other compiler into it.
Yep. So let's talk about code generation and talk about accelerators and how this all works. So if you look at a modern device, for example, a cell phone, it's already completely heterogeneous. And so you may have multiple CPUs on your phone. You certainly have a GPU. You probably have an inference accelerator if your phone's new enough. You certainly have an ISP for video and JPEG decode and DSPs and lots of other stuff. In TensorFlow right now, its general design is really well set out to handle heterogeneous compute.
Okay. And so we need really powerful code generation to handle all possible heterogeneous accelerators, which we can think about. And so we are investing into two approaches, XLA and Polyhedral.
Yep. So we'll talk about each of these. So XLA is a really great compiler. There's a talk by Thomas, I think it's later today, to talk about some of this. The way XLA works is effectively by having this high-level graph of operations that work on tensors. It provides algebraic optimizations. It does buffer assignment and layout assignment. It decides to fuse operations. And then after doing a bunch of graph-level optimizations, it uses this emitter design to generate LLVM or other target code from this optimized graph.
One of the key optimizations in XLA is fusion. And it's not as simple as fusing convolution to D with followed up bias add. It really fuses subgraph to generate very efficient code. And this is where a lot of XLA power comes from.
Yeah, it's really impressive. Reductions, element-wise ops, of course, but the XLA is very powerful in this space. And so if you look at what XLA is doing, right now it's already quite industry-proven. There are other folks that are inspired by its design. Google is using it pervasively for TPUs, which are machine learning accelerators. And the GPU work, which you'll learn about later, is also really promising. The challenge with the XLA approach, though, is that it works really, really well if it knows all of the operators, and so it knows intrinsically what those ops are. And in the machine learning research world, they want to experiment with custom operations and want to have hardware-accelerated, flexible programming models for getting high performance out of this wide range of heterogeneous accelerators.
And so to handle custom operations, we turn to polyhedral compiler techniques. Now, polyhedral has been around for quite a while. It has great success in high-performance computing for image kernels. It had less of success in the general field. Fortunately, we are not dealing with the general field. We are dealing with tensor operations, which are quite regular and amendable to expression via polyhedral. Polyhedral is great because it gives us solid mathematical foundations. It's not so great because it's complex. But what we try to do here is to keep all the benefits from polyhedral while significantly reducing the complexity.
And so what we've done is we've taken the math and the ideas and boiled polyhedral down to its essence and looked at what makes the dependence analysis super popular or super powerful and predictable, what makes the transformations closed under their own transformations, and have looked to solve the downsides of polyhedral. So we've come up with a new form. We call it the simplified polyhedral form. And when you look at MLIR, you'll see it looks just like for loops and if statements. And so one of the things about this is that the for loops and if statements are represented as regions in MLIR. These are just user-defined operations, just like anything else. And so our polyhedral approach is just an affine dialect in MLIR.
So what simplified polyhedral form gives us is, of course, simplicity. It's seamlessly integrated in the IR. It supports SSA. It's accessible to people if you looked at the code on the previous slide, there is no word polyhedral there. There is no schedule trees there. It's actually code that any engineer can read. And we don't use polyhedral code generation with exponential algorithms. We just do it in a normal, simple code generation way.
Yep, and so scalability is the key. So we support very large models. So this work is still quite early, but we already have a number of great passes with like Unroll and Jam and vectorization and other things well underway. And so if you're interested, take a look at this. And so I think people often ask me, which approach is best? And why are you investing in two different things? Why XLA and Polyhedral? And the short answer is that there aren't even just two ways. There's actually a lot of different ways of generating code, and this is just for tensors. There's the halide and stripe approaches, which are also really great. Apparently people still write kernels by hand. That's a thing. That's actually one of the most popular ways. And all these different approaches have different trade-offs. And so if you have a specific kind of a hardware, well, one algorithm might be better than the other. And at the end of the day, users don't care. They just want to walk up to an accelerator framework and have it go fast. And so our approach is to say, well, we'll have one common infrastructure, and we can use the best algorithms for the use case at hand. And if Polyhedral is better for one case, the XLA algorithms, the stripe algorithms, a custom handwritten kernel is better for this use case, well, fine. We can actually measure and choose empirically based on data instead of based on the whims of an engineering team.
Okay. So now, if you remember in the beginning of the talk, we said that MLIR is actually not machine learning intermediate representation, it's multi-level intermediate representation. And that means that it can be applied to things which have nothing to do with machine learning, as Clang.
Yeah, and so Clang we mentioned before. So let's talk about what a high-level IR could look like in Clang. And this is very much following the Swift SIL design. This is totally strawman, nothing super serious here. But one of the things that you start to think about when you work on C++, like probably we all do too much, is that we have all these manual things we have to do to get good performance. Like you have to reserve space in an array if you're going to fill it in, or in a vector. Well, it turns out dataflow analysis can identify things like this and could call reserve for us. The problem with doing this on the Clang ASTs is that you need dataflow information. The problem with doing this on LLVM IR is that you've now lowered down the fact that like vector gets passed by value, and so that gets passed in an SSE register or something crazy. And so it becomes very difficult to do the analysis that you want. And so one of the things we found with the Swift IR is that by using the type system as a first-class thing in the compiler, you can now model these things directly. And you should call std vector pushback and pass it a pointer to the vector type. And it should be the Clang vector type, or std vector type. And the fact that MLIR has this extensible type system, and you can have domain-specific type systems, and you don't have to re-implement them, is a huge part of this power. And so we think this can be really useful for lots of different things. And so optimizations are one piece of this. For example, wouldn't it be great to be able to optimize capture lists and closures, or lambdas? Wouldn't it be great to be able to say, here's an attribute, you put it on your value type in Clang, and you promise that it has value semantics, and now it can optimize all the copy constructors and everything out for you. The Clang world has the CFG data structure, which is used by dataflow warnings and the Clang stack analyzer. Always incomplete, and it's always under-tested because code generation doesn't use it. We can and should fix that. And it's also a hugely requested feature to be able to share ABI lowering information from the C world to targets. And this would be a very easy and natural way to do that because of the lowering infra we've built.
So one thing that we can use MLIR for is OpenMP. So one of the challenges with handling OpenMP today is that outlining is done early, so the body of parallel for loops, because as a function now everything is interprocedural analysis. In the MLIR we have nested regions. So we can use regions to naturally express OpenMP pragmas, and now everything is easy because everything is within the scope of a single function.
Yeah, and this is a great example to me of a problem we have in the LLVM community where most people care about Clang for many reasons, but in the Clang world, we have now two choices which are often unfortunate, either the AST, where you don't have data flow information, or LLVM, where you've done a lot of lowering. And so having a level in between that would be, I think, really powerful. And OpenMP is one example of that, because right now, my understanding is the Fortran, the Flang people, are talking about generating Clang ASTs to be able to get OpenMP, and this just makes my head explode. Like this is F to C all over again, and we need to find a good way to do this. But there's also lots of other things going on. Like it frustrates me that the ARM community is struggling with getting scalable vectors into LLVM because LLVM really doesn't like variable size types. Well, obviously that's no problem for us, and representing something in a first-class way and then lowering to what LLVM and what LLVM is good for would be a very natural thing to do. Other folks in the LLVM community are trying to get two-dimensional vectors. Again, that's totally simple for us because of, first we're focused on that stuff, but also because the whole system is extensible. And there's tons of high-level optimizations that there's just really no good place to do in the stack today. And we'd love to see this go further and move compilers ahead and reduce some of the pressure of just cramming everything into LLVM IR, which is not great for LLVM either.
Okay, so now we'll talk of how everybody can get involved with this. I'm really happy to say that as of last Wednesday, MLIR is in the open source, so please check it out on the GitHub. There is documentation there is examples, then there is code. Please join our mailing list, and be warned, this is early. We put it into open source. We'd love to take contributions, just not yet because we don't have the infrastructure set up for this. And some parts of what we talked about, which relate to TensorFlow, are not in the open source yet, and this is just a matter of time as we are preparing the code for release.
Yeah, and so one of the things we're very curious about is we're curious if the LLVM world would be interested in some of this technology, and so we're planning to start a thread on LLVM dev or wherever it's appropriate to see if anybody would like to add this as a new subproject to LLVM. So, if you're here today in person, then we have a bunch of stuff going on to talk about MLIR. So there's a great tutorial that I hope they'll have done by tomorrow to talk about how to actually use this, show building a compiler. It shows how to generate array IR and optimize it, and that's tomorrow at noon. Also, there's a roundtable later today to talk about this. And we are an inclusive community, so even if you're not Poly Labs, you're very much welcome to come there. And we have lots of people that are here today. And so we're actively hiring. If you're interested in working on this, please join us. But otherwise, thank you. And are there any questions?
So for questions, please move to the mics in the middle of the...
Hey, great talk. So I basically have a question. You present this, like the Polyhedral stuff, the OpenMP stuff, as a new way of representing things inside the IR, which it seems to be, right? But only representing it inside the IR doesn't necessarily solve the problem, because you say Polyhedral is it's not exponential anymore, but dependency testing is exponential. There is no way around that. Like if you want to know what you depend on, what a load in a certain iteration depends on, you always have to look at all the potential candidates and then decide which one it is. Like the representation of I have a first level affine loop doesn't change that. Yeah. It changes other things.
So I think you're asking specifically about the polyhedral stuff. So dependence testing is not exponential. So it can be n squared if you choose to do all pairs. The choice of algorithm, there's a wide body of work on different dependence testing infrastructures. What we've done is our approach to polyhedral is different than the standard infrastructures. We don't use ISL, we don't use exponential time polyhedral code generation. There's lots of details. Happy to talk about that. Maybe not the best thing with a wide audience to dive into, but we can talk about that.
Okay.
I think your point still is very valid though, right? I mean, you can choose within this infrastructure to implement whatever algorithms you want. And so
Let's go to the OpenMP thing then. So you say, sure. Okay, we do OpenMP parallel regions, a OpenMP parallel force as a first level citizen in the IR, and then constant propagation is just going to happen. So there are a lot of folks that currently propose different variations of putting OpenMP parallel force as first level citizens into LLVM IR, and all of those things are flawed in one way or another, because it will break apart.
Yes.
And just doing that here, like all the optimizations you want to run on it have to be aware of the fact that there is parallelism. So you basically can't reuse the optimization we have.
Yeah, so that gets into how we represent region semantics in MLIR, which we didn't have time to get into, but we're happy to talk about that as well. So, but yes, I agree with you that all the implementations in LLVM are problematic.
Well, This looks like it'd be really useful for dealing with things that are currently like backends for LLVM for different IRs. So like SPV, the other ones like there's Microsoft for the DirectX one. Do you see that? Do you see this being useful for that going forward?
I'm sorry, can you restate the question?
Currently, I use LLVM for targeting other IRs that I have backends that are not backends for LLVM, like SPV for OpenCL and Falcon and other things. Do you see this being a useful infrastructure for dealing with those kind of things, separating them from
So our goal here, so it's a very general IR, you can do lots of different things, you have lots of design space, but LLVM is really good at targeting code gen, CPUs, GPUs, and dealing with that C with vectors kind of abstraction and down. We have no plans to re-implement any of that stuff. LLVM is awesome, so we're not interested in replicating that. And if you're using LLVM and you're happy with it, that's awesome. Right, we are too.
This is more about dealing with IR to IR transformation, so LLVM IR to SPV, LLVM IR to DirectX, DX12, whatever, that are currently sort of backends, but not really backends. Do you see MLIR being a sort of...
I see you're talking about PTX,
lingua franca for intermediate
PTX and Scriptin and all the other things that are not really...
Not really backends, but kind of.
I mean, you could choose to do either. I personally have not thought deeply about what the best way to do in Scriptin or one of these things is. So I don't know. Yeah.
Just a quick comment. I'm the Clang guy, and no, we don't lower OpenMP into Clang ASTs. We generate code.
Okay.
Like we should.
Thank you.
Hi, thanks for the great talks. So you explained that you use some kind of dialects to prevent your IR becomes more adjacent, but does that mean that like eventually you need to write like different optimizations for like different kind of dialects? Because I think you try to solve this problem in the like table chain. Like I saw there's a line saying that okay, you can define your own constant propagation on the table chain. Is that true? Is that how you solve? Yeah.
Yeah. No, you don't need to write the same optimization multiple times. So for example, for constant folding, right, you write constant folding once, then you can specialize how instruction is being constant folded, and then if you want to outsource it, as in the case of TensorFlow dialect or TensorFlow runtime, then you specify it as a hooked on the dialect, but the optimization itself is written once. You just rewrite customizable pieces of it.
So does that imply...
This depends on the optimization itself, and so it is very much possible and very much encouraged to write dialect-specific optimizations. And so if you're doing something to optimize Clang STD vectors, there may be zero reuse with some other dialect, and so that's fine. Just make it completely concrete and work on exactly the operations you expect. That's no problem. But we found that there's a lot of optimizations, both the simple ones like constant folding, but also bread and butter ones like common sub-expression, elimination, loop invariant code motion. They get parameterized based on properties, and so with CSE, for example, you just want to know, is this thing commutative? If so, then I can swap it around and I can match and value number it in different ways. And so by defining properties on the operations, you can get a lot more generic code and a lot more reuse. Inlining is another one.
So like for example, for those simplers, like do you like write using some kind of DSL like or similar things?
We write very LLVM style, and so it depends.
Okay.
So the equivalent of ints combine, or sil combine, or people optimizer, or dag combine, like the equivalent of that is we have one pass, and then each operation that you defines a list of canonicalizations. And so there's one canonicalized pass that works on any dialect, and then for every operation you say, okay, well I'm gonna multiply, like x times 1 is x. And so the operation itself defines the patterns, and then the pattern matching infrastructure kicks in, and there's a top-level loop that applies the cost model and does all that kind of stuff, but it doesn't know what the semantics of the operations are.
Yeah. So, like in general, it depends on the properties, right? Like,
yeah.
Okay.
Yeah. And so, I look at this as an engineering optimization trade-off thing, where you can still write completely dialect-specific passes if you want, and you could use only that, and that's fine. But there's a lot of reuse, and there's different kinds of ways of factoring commonality across these domains. And if you write a devirtualization pass, for example, it's very likely to want to work on your very high-level AST kind of representation, or source type system representation. And Swift and Clang and Rust and like all these things all look different now. But you can define like a virtual interface that knows which operations are particular to that language, define the subtyping rules, and define an abstraction that makes sense for devirtualization, and then potentially share a bunch of that code.
Yeah.
We haven't worked on devirtualization
So
specifically.
just one last like
That's
quick
the
question. So like I think, do you have like a documentation on the table gen part? Because I think that's the core parts of this framework.
Yeah, we actually have, I mean, we're still early on, but we have a bunch of documentation under the G3 docs directory in the repository and on GitHub.
Okay, nice, thanks.
Yep.
Any